Let me demonstrate my screen and rotate it. Okay. So today we continue to discuss an example of the structure of the stochastic semigroups. And last time we discussed that stochastic semigroup can satisfy a linear stochastic differential equation. And it was mentioned that in case when our Hilbert space is L2, it does not matter on R, on RD, and we have the following stochastic differential equation G OTH is L G OTH dt plus B G OTH dw T when A and B are differential operators. L is elliptic operator. B is first order. First order linear operator. Differential operator. Then we must have a relationship like L is minus L is greater or equal than to B convolution with B, which is also will be a second order operator. But of course, if we substitute the pair L and B onto bounded operators, bounded linear operators, operators in Hilbert space, then one can consider the arbitrary structure of this Hilbert space and discuss the same stochastic differential equation dJOTH is equal H JOTH dt plus B JOTH dWt, and in this case the solution always exists and is stochastic semigroup. And is a stochastic semigroup. And in this case, as we began to discuss yesterday, these elements of the equation, like operator A, operator B, together with Wt, can be recovered from our stochastic semigroup J. Namely, it can be proved that if A and B, if A and B are bounded operators, so they belong to the set of bounded operators in H. Then there exist limits. A limit. A limit. Let me tell it denoted by eta t, eta h t, which is equal to limit when t k maximum, when maximum uh, okay, tk plus 1 minus tk tends to 0, of the sum which we already wrote yesterday, which is equal to sum from k equals 0 to n minus 1. Here is j tk plus 1, h minus h, and moreover, it can be written. As a sum as eta ht occurs to be equal at h. Maybe better to write in backward direction because t is scalar now, a is operator. So TAH plus WT. It depends on which kind of inner process we are considering. If we consider a Hilbert-valued Wiener process, we of course cannot change it in this way. But if we have just one-dimensional Wiener process, we can put it here. BH. That's all. Okay. One can recover noise, one can recover operators A and B from our semigroup, and our semigroup has this good structure as a Hilbert operator valued stochastic exponent. Only one thing which we have to keep in mind is that if A and B are unbounded, we have to be careful with the condition which we already mentioned, that operator A must dominate in some sense operator B. But it occurs that the structure of the stochastic semigroup can be much more complicated. And today in my lecture, I will show you two examples which are essentially infinitely dimensional and in which the semigroup cannot be obtained as a solution to any linear stochastic differential equation. Does not matter with bounded or unbounded operators. So let us begin with the example which was discovered by me in 2011, and this example can be called semigroup. Excuse me, semigroup of finite dimensional projections. So let us fix our Hilbert space H, which is as before. real separable Hilbert space. Then one can try to consider stochastic semigroup of special kind. Suppose that JST JST is a stochastic semigroup semigroup in H in H such that here I will put additional by the sentence that JST is a stochastic semigroup. I am supposing that J satisfy all the mentioned conditions. So we have the independence on the non-intersecting time intervals. We have equidistributions for the time intervals of the same length. We have the continuity at zero in probability or in square mean. And the important thing, we have evolutionary property. Yeah. But now I additionally suppose that uh, for arbitrary uh, zero less or equal than s, less than t, strongly less than t, j s t is finite dimensional projection. Projection. Of course, it is random. So it means that for all omega from the probability space, our J S T, let me put omega here, is a projection. Always when I say projection in Hilbert space, and I mean orthogonal projection, of course, is a projection. And dimension of JST is omega from H, so dimension of its image of the subspace on which JST project all space is less than infinity. Okay. So maybe before we proceed further, let us imagine at least one finite dimensional projection in infinitely dimensional space. How we can do this? Let us begin with example of finite dimensional projection. Suppose that En n is greater or equal than 1 is orthonormal basis in H uh, fix n 0 greater or equal than 1, so fix some natural number, and then uh, uh, define the projection Q as follows. For all x small which belong to our Hilbert space, define a Q of x is equal to sum from k equal 1 to n0 x e n excuse me, not n but e k e k. In terms of operators and tensor products, Q now is equal to sum from k equal 1 to n0 ek tensor ek. So the construction of the projection is very simple. We just take the orthogonal basis in our Hilbert space and organize the action of the projection as a killing of all coordinates except some finite number. And of course, this is only my choice that I choose the first coordinates for construction of Q. Maybe everybody understands that I can choose arbitrary finite subset of the natural numbers as numbers of coordinates which remain to be alive under our projection Q. And this gives us the idea how to construct the infinite dimension, the semigroup of such projections. So, the construction of semigroup. Take a sequence lambda k is greater or equal than 1, be a sequence O positive numbers such that for all t greater than 0, such series sum from k equal 1 to infinity e lambda k t minus lambda k t converge. Mhm. One can easily construct such numbers, uh, and then uh, let us take a sequence, take a sequence uh, nk t. T is greater or equals than 0, k is greater or equals than 1, uh, independent, independent with processes or Poisson processes uh, with intensities lambda k. Then define define uh, for k is greater or equal than 0 than 1, 0 less or equals than s less or equals than t, uh, the following number new uh, s t k equal to 1 if n t minus ns is equal to excuse me nks equal to 0, and 0 in opposite case nkt minus nks is greater than 0. Then finally define put our semigroup operators j excuse me q j s t, just a sum from n from k equal 1 to infinity. Uh, Here is new s t k and e k e k. Let us understand what is it. What does it mean? This construction. Uh, so any process nk calculates random events. As we know, Poissonian process is counting process for uh, homogeneous flow of random events. And these events happen independently for different coordinates. And our semigroup is constructed as follows. At any time interval st, we just kill such coordinates for which a random event of from the corresponding flow occurs at the time interval st, and it does not matter how many. Occurs one, it is enough. These are killing events. So if we have just one, then we kill this coordinate. And you see now this condition. What does it mean? It exactly means that uh, uh, we have the following. Now, the sum of probabilities, uh, sum from k equal 1 to infinity of probability that uh, new st k is equal to 1, so that no events occurs. Yes, this is exactly the probability that here is written probability that on the interval 0t no events occurs from the k Poissonian flow. So now we have this one which is less than by the condition. Then by Borel-Cantelli lemma, it follows it follows now from Borel-Cantelli lemma that uh, JST is a finite dimensional with probability 1. Uh, so maybe it is easy to check due to additivity of Poissonian flows that JST satisfies evolutionary property, and it is also a technical exercise to check that JST is continuous in square mean at the point 0. In this way, we get a family of finite dimensional projections, random projections, which are a stochastic semigroup, which are a stochastic semigroup. Uh, moreover, moreover, you see what happened. Here we have very interesting thing. Uh, all representative of our family JST are finite dimensional. And what we have uh, in in probability for all in probability J O T H converge to H when t tends to 0 plus. Please check this. Also, this can be checked, yeah? Using usual calculus, it is very trivial. And Lebesgue dominated convergence theorem. What does it mean? That we have the picture which is purely stochastic. Our space H is infinitely dimensional. And we just have the semigroup of finite dimensional projections which approximate the identity. Yes, at the point 0. Yeah, at the point 0. And please check that we cannot organize deterministic semigroup of finite dimensional projections which will have such property. So this can be a good exercise. Check that there are no deterministic semigroup of finite dimensional projections at all in infinitely dimensional space. Yeah, which approximate our identity, which is continuous at the point zero. Nevertheless, one can go further. Maybe those of you who just studied probability theory recently were slightly, at least have some question relatively to using of Borel-Cantelli lemma, because everybody remember that Borel-Cantelli lemma consists of two parts. One is related to the statement which I use. So if we have some sequence of random events like we have here, and the probabilities of these events organize a convergence series, then only finite number of such events occurs with probability 1. And here we don't use the independence of these events. Yeah, it is just statement which can be applied to arbitrary sequence of random events. But we have another statement from Borel-Cantelli lemma, which shows if that series diverge and we have independent random events, then they occur infinitely often with probability 1. So we have almost backward statement. And to understand that in my examples of the stochastic semigroup, there are no non-useful things because we have this statement that we have independency of coordinates. Let me propose to use a theorem which also proved by me in the same paper 2011, the following. This theorem says that if JST is a stochastic semigroup, of finite dimensional projections, then let us let be more precise. In H, then it has described above structure. You see, it occurs that our construction, which we considered before, and which contains orthogonal basis, independent Poissonian processes, with specially organized intensities, is general. It occurs that any stochastic semigroup of finite dimensional projection has such structure. Uh, but to prove such theorem, we need some statement about structure of commuting self-adjoint operators and so on. So we will not uh, consider the uh, proof of this theorem. But let me tell you that maybe everybody understand that such limit now will not give you, at least will not give you a Wiener process and some good continuous semi-martingale. There are some approaches which can allow you to recover even such bad noise like Poissonian, such discrete, I must say, noise as like Poissonian noise in this case. But this is not a subject of our consideration right now. Instead of this, I promised to you to show you another one example of the very interesting stochastic semigroup consisting of strong random linear operators for which one can also recover the stochastic differential equation. So this another example is based on the so-called Aratia web. So let us write the title of the next small section: stochastic semigroup related to Aratia web. Here, let me recall you what does it mean Aratia web and how it is constructed. So let us start from two Wiener processes. Let W and 1 and W2 are independent standard Wiener process on the real line. On the real line. Then one can suppose that W 1 0 is less than W 2 0. Then one can define this following moment, the following stopping time. This is an, excuse me, this will be a minimum of such t which is greater than 0. The W1t is equal to W2t. And also it will be, it is well known. And for those of you who don't know this, it will be a very good exercise from stochastic process theory that probability that tau is less than infinity is 1. Then one can define the following processes. X1t will be equal to W1t for all t which is greater or equal than 0. And x2t will be equal to W2t multiplied on the indicator that t is less than tau plus W1t multiplied on the indicator that t is greater or equal than tau. And you see what happened. We just do the following. We have two winner processes. For example, this is our W1t, W1, and this is our W2, W2. And what we are doing, we just subtract W2 after the meeting. And we suppose that after the meeting, both processes are going together. And we even rename these processes and tell that these new processes will be x1 and x2. What is interesting? It occurs that x1 and x1, x2 are again winner process. Are winner processes. So after such gluing, they remain to be winner. It is a consequence of so-called strong Markov property of the winner processes. Then one can maybe understand, and this is trivial, that one can proceed in the, one can proceed in the same way, having a arbitrary number of the winner processes. So one can glue up not only two winner processes, but also arbitrary number of the winner processes. In this way, one can get a family of winner processes which are independent up to the meeting and coalesce after the first collision. It occurs that the finite dimensional distribution related to the starting point un, yeah, are consistent. So if we add another one, for example, un plus 1 here and glue up it, then we have the distribution which from the same family. Then by Kolmogorov theorem, theorem about the family of consistent distribution give us that there exists a family of coalescing winner processes starting from it is important every point of the real line and I will I will denote this. Okay. I will denote this family XUT. XUT. Here U belong to R. T is greater or equal than 0. So for every fixed U, XUT is a Wiener process. If we take finite family of starting point, then corresponding process X are Wiener process independent up to the meeting, then coalesce and move together. This family is called Aratia flow. It is called Aratia flow. Flow by the name of Richard Aratia, who discovered it in his PhD thesis in 1979. Since then, a lot of authors pay attention to this flow. Even there are different constructions. In his initial thesis, Aratia gets this flow as a scaling limit of coalescing random walks on the real line. In my case, I got it like a limit of the smooth flows related to stochastic differential equation with the blowing up diffusion part. And there are a lot of different constructions. But what is interesting, one can go further and construct not only Aratia flow, but Aratia web. What does it mean? It means that one can consider not only starting point on the real line. So how we did before, we construct this one, yeah? But one can consider also starting point at any moment of the time S, for example, and do the same. Checking the previous trajectories. Here, of course, we will use the properties of Aratia flow. For example, it can be proved that at any positive moment of the time, the old trajectories organize only discrete set in this real line. So if we consider trajectories which start at the time 0, then we have only discrete set of the different trajectories which intersect the time horizon S. This allows us to construct the more complicated picture consisting of Brownian of Wiener Wiener processes which start at any moment of the time, not only at the time 0. In this way, we get the following family: phi st u. Here, u belong to R is a starting point, and S is a starting time, and T is an instant time now. Yeah? And this phi st has a good properties. For example, they are independent for S for non-intersecting time intervals, equidistributed as random mappings, and so on. This family is called is called by Aratia Web. By Aratia Web. Okay. Unfortunately, today I have to finish my lecture 10 minutes before hour because here we have a conference where I am a chairman of the session. So we will continue at Friday. For today, that's all. Thank you for your attention.